In this video we'll be talking about Castigliano's theorem. So Castigliano's theorem, it states that the deflection of the elastic structure subjected to a number of loads at the point of load application is equal to the partial derivative of the total strain energy with respect to that load. So basically what it says is the deflection at a point is equals to the partial derivative of the total strain with respect to that force. That is the basic idea of Castigliano's theorem. So if we look at the equation, the deflection delta, which is equals to da by u by da by f. So u is the total strain energy in the structure, f is the applied load, and delta is the displacement under the applied load. So for example, let's take a simple bar in uniaxial direction. Okay. So now if you look at if you apply a force F in both sides, the stress, which is equals to force divided by area, and the strain energy, which is U, is equals to half sigma squared divided by E into area times the length. So you can take as U as now if you look at the stress is equals to force divided by area, so we can write in the stress is basically F divided by A, so the square term of the sigma, which will be equal to F squared divided by A squared. So when you multiply this U, which is equal to F squared AL divided by 2 A squared E, and we can take, after dividing A with A, we can take it as F squared L divided by 2E. So since the deflection, which is equals to the strain energy, the partial derivative of the strain energy with respect to force, therefore we can take the partial derivative with respect to F force. So if we differentiate this value, the equation becomes, after differentiating you get delta, which is equal to FL divided by AE, or you can write the F as length into the strain. So deflection of the beams using Castigliano's theorem, since the total strain energy is given by UB, which is equals to integral of m squared divided by 2EI dx, we can write like this. So if it's possible to determine the deflection due to an applied load by y equals da by u divided by da by w. So now look at the sign convention. So look at the change in notations. W is applied to the load, and x or y is the deflection vertically or horizontally respective. You can write therefore da by u divided by da by w, which is equals to da by integral m square divided by 2EI ds, divide the whole thing divided by da by w. So you can write, ultimately you can write y, which is equals to 1 over 1 divided by EI, which is the multiple of integral of m divided into da by m by da by w ds. So it is quite common to want to calculate the deflection of a beam in the horizontal axis when only a vertical load is applied. So basically what you do here is it is quite common to calculate the deflection of the beam in the horizontal axis when only vertical load is applied. To carry this out, a unit load H is applied, which is unknown value. So basically the unit load horizontal value will be applied, which is, we do not know the horizontal value. So x, which is equals to dA by u divided by dA by h. So after following this procedure, equations containing h are eliminated and the resulting deflection can be determined. Also note that this method can be employed to determine the unknown value of h if the beam is restricted. So you can see that this delta h term can be eliminated. So resulting deflection can be determined. So we will look at the sample member. Okay. Determine an expression for the horizontal displacement of the member shown below. So it has a L-shaped beam and the length is L, and also the vertical length is L divided by 4. So we can take from 3 points x, y and z. So x is the starting point, y is the intermediate point, and z is the ultimate point. So now if you resolve these forces, the reaction force is F and the moment is F into L divided by 4. So the strain energy is a scalar and therefore separate strain energy quantities can be developed and added together before proceeding to use Castigliano's theorem. So from the Castigliano's theorem we have deflection, which is equals to 1 divided by EI integral of m into dA by m or dA by f dx. So now if you look at previously from x to y, we start from point x goes to point y. So moment is equals to f into x. So basically we take a general point and we evaluate it through x to y. So from x to y you have m, which is equals to fx, and dA by n more dA by f is x, because we differentiate with respect to f. From y to z, moment is equals to is a constant value. So if you take it as dA by m more dA by f, which is equals to L divided by 4. So y, this displacement is basically integral of from 0 to L by 4 m dA by m more dA by f dx plus the integral of L to 0 dA by m by dA by f dx. So you have x to y component as well as y to z component. So now if you integrate this to solutions, you can look at it like this. So y is equals to 1 over EI integral fx square dx integrated from 0 to L by L divided by 4 plus 1 over EI 0 to L fl square divided by 16 dx. Integrating we get y, which is equals to 1 over EI fx cube divided by 3, which is integrated from 0 to L divided by 4, and fl squared x divided by 16 from 0 to L. So you get the final displacement as y equals 13 fl cube divided by 192 EI. So for as a example, determine an expression for the vertical displacement under an applied load F.